Hey, welcome to Ones and Zeros. My name's Ben, and today we're going to be looking at part 2, episode 2 of our Discovering STM32 series. So we're going to follow on from where we're up to at the end of the last stream or last video. And now that we've got the microcontroller up and running, got all of the clocks sorted out, got the LED flashing, and all of that basis of everything sorted out, we're going to look at getting a bit of code done in order to make it a bit easier to work with the GPIOs. So we'll be looking at doing some stuff with both the LEDs and the user button, which is not going to take us too long. Following that, we are going to be looking at getting the UART working so that we can actually get serial data back to the laptop and use both the LEDs and the serial for being able to debug things a little bit easier as we move further along with the code for this one. Anyone that's interested in the STM32 range in general, a lot of the stuff that we're going to be looking at today does work for most of the STM32 family. There is some sort of little quirks as far as how registers work and things like that. But we'll have a bit of a look at that as we go on. After this stream, looking at where we're going after this one, we're going to be doing a couple more streams of this particular series next week, looking into getting the SD-RAM up and running and the LTDC and DSI so that we can actually get some stuff being displayed on the LCD screen, as well as looking at writing some methods or some code to be able to get text and different graphics and things being drawn onto the screen so that we can also start to use that a little more. Following on from that, we're going to be looking at getting some of the other peripherals up and running, so random number generator, real-time clock. Might even look at getting the analog to digital converters and encoder working on the other board that we've got here with the joysticks and stuff on it. So again, that sort of stuff will also be relevant to some of the other STM32 family as well. So a bit of stuff there, and we're also going to be looking at getting another series started next week, looking at the expressive ESP32 range. We're going to be doing that using the Arduino IDE, so be a bit of stuff that we're going to start looking at there. And following on from that, in probably a couple of weeks, we're also going to be looking at starting a series where we're looking at FPGA development, and all three of the series will actually be going side by side. Part of the reason for that is because we're actually going to, in the future down the road, looking at getting all of those devices talking to each other and working together as a big team so that we can start to make some really cool stuff that we might not be able to do just with one device. So if we pull up the code that we were working with last time, we can see, as you may remember if you saw that stream, we went through and got all of our boot code done so that we're getting everything set up, all of our clocks set up and things like that, so that everything's good to go. And by the end of the stream, had the LED flashing so that we could see that that code was actually working correctly. You might notice if you saw the last stream, I've actually got the camera working a bit better for the discovery board this time, so the LED is actually flashing the way it's supposed to rather than a massive delay there. But anyway, enough talking. We might get stuck into writing some code and see what we can do here. So in order to get the LEDs working at the end of the last stream, we basically just initialized all of this in our main.cpp and put a bit of delay code in there in the while loop in order to make that flash once a second. So one of the other things we're going to be looking at during this stream, once we've got the GPIO code done the way we want it, is we're also going to be looking at a particular way that we'll be able to start to time things in the while loop a little bit better. So in this case, while we've got our HAL delay 500 here, we're actually wasting a bunch of the CPU's time because it's sitting there doing nothing for 1 second every loop because it's just sitting there being delayed. So we're going to look at a way that will allow us to be able to run multiple tasks, each with a slightly different timing as needed. Now, first things first is we're going to get a folder created. We're going to create a folder in our project just for our driver code. So basically any of the code that is dealing with the on-chip peripherals, so on the F7 chip itself. We're also going to be putting stuff in there that deals with things like the SDRAM and other peripherals that are on the board, just to keep things a little more organized. And that basically goes for anything that's either directly talking to peripherals or stuff that is talking to them via the HAL. And again, as mentioned last time, we're going to have a bit of a look at both doing code with the HAL as well as doing direct register access as well as we progress further through this series. So we're going to create a folder here, just like that, and we're going to call him QA drivers. Again, QA being the letters for our project name that we're using for this one, which is Quartz Arc, just so that we know a bit better what we're dealing with. So we're going to jump into our project properties first up and set up our folders so that it knows to treat that QA drivers folder as both a source and an include location. We're not going to look at doing that for C code. We're only going to be doing that for C++ because there's nothing in there that's going to be C. So we're just going to add that one in there. Like so. We're also going to do that for our release configuration as well. And we're just going to pop that in as a source location as well. And apply that. Just like that. Alright, so in here, we're going to start by creating a couple of files. We might do this the easy way. Create a... It's not giving me the normal options. That's a bit weird. Let's see if we've actually done this correctly when we set up the folders here. There we go. Try that. That's a bit better. So because we didn't have it added properly as a source location, it wasn't giving us the option to be able to come in and just select a header or a source file. So for this one, we're going to call it QAD. So for Quartz Arc, and then the D will indicate that it's driver code, just again, so we can see stuff nice and easily at a glance. And we're just going to call this one GPIO.hpp. That'll be that header file, and then we're going to create our source CPP file to go along with that. So qad.gpio.cpp, like so. Get rid of the template code there. And what we might do, just so that we can get our header done nice and easily, so we're just going to copy and paste that guy in there. The system for this one will be drivers, as it's part of the driver code, and the role for this one is GPIO driver. Now, what we're going to be doing with this one to make life a little bit easier is actually be using a C++ class to create our GPIO driver. So a single class will allow us to access a single pin. We're going to make one class for output, so using those to control the two user LEDs, as well as a few other things that we're going to end up hooking up to the discovery board. And then we're also going to do a class that is specific to input from a GPIO. So we're going to be using that for the user button, and we'll be using that for some of the other buttons and things once we move on as well. So with this one, we're just going to update the date on that. So we've got the 24th today. And we're going to make sure we pop in our stuff to prevent recursive inclusion. So if not defined, actually I didn't update the file name. We'll just quickly do that as well. So QAD GPIO.hpp. And define that one. Like so. Alright, we're also going to pop in here our setup.hpp, and that will then include the STM32 F7 files that give us access to the HAL. So that way we don't have to worry about any other bits there. And now that we've got that bit, let's copy and paste that into here. I'm just going to, might help if I hit the right button. There we go. Delete that there, and then we're going to include our QAD.GPIO here. And we'll just change this one to be a CPP file so that we've got the header correct there. Excellent. Now, to start off with, what we're going to do is basically just do the first class completely in the header file, and then we will move the class methods out to the CPP file. So that way, by the time we're done with it, we're just going to have our declarations in the header file and our definitions in the CPP file, which is the nice, neat way to do it. But to make things a little bit easier, make it a bit easier to see everything all in one spot for the moment, we're just going to look at doing it in the header file initially. So we're going to just making sure everything is working correctly, which it looks like it is. Wonderful. All right, let's get our class created. So we're going to go with QAD GPIO Output will be our class name. Now the beauty of doing it this way is it does mean that we can use the same class for multiple pins, which allows a little bit more flexibility than doing it just with raw code or not using an object-oriented approach. As I mentioned in the last stream, I'm a bit of a fan of actually doing both ways. Although I prefer C++ as a language, I do really like C. It's a very close second as far as my favorite programming language. So we're just going to create a private and public section in that class for the moment. Now, because we're going to get our GPIO will be initialized when the class is created, and the GPIO will be set back to default settings when the class is destroyed. We need to be able to provide the class with a couple of bits of information for the constructor so that it can actually go through and do things correctly. And those bits of info will be the GPIO itself, so which GPIO that pin is on, as well as which number that pin is as well. So we need to make sure that our default constructor is not accessible. So we're just going to take our default constructor and delete that one. And we're going to create another one that allows us to take in a, I believe it's GPIO type def. I could be wrong on that one. That looks correct. And that's that one. And we're also going to pop a uint16t in there, which is what we use to identify which pin we're dealing with. Now we'll just close that off for a second, and we're also going to come in here and we're going to create a couple of private variables. The first being the one that will actually hold our GPIO, like so, and one that will hold which pin we're actually using. Now we're going to create another one as well to keep track of what state the pin is in, whether it's on or whether it's off. And that'll make a little bit more sense when we look at being able to retrieve from the class what state the pin's in, as well as doing things like toggling the pin. So although there is a HAL method or HAL function to be able to toggle the pin as well as turn it on and off, we're not going to be using that because of the fact that we'll be keeping track of it ourselves. Now what we're going to do for that one, and we're going to pop another public section up here and create an enum in here. And we're going to use an enum to actually track whether the pin is off or pin is on. So we're just going to call this guy pin state and make him a uint8t, and we'll go with pin off equals 0 and pin on, which will end up equaling 1, which allows us just to go in and create pin state and go with the e state. Actually, let's fix this up so that we know that they're actually member variables. So just pop the m underscore in front of those, keep things a little bit easier to understand. Now we could just come in here and go mp GPIO equals p GPIO in order to save what's coming in here into the member variable. However, I'm a bit more of a fan of using member initializer lists. So in order to do that, we're going to pop in a colon there, a little bit of an indent, and we'll go m underscore p GPIO like that. We'll do our pin, so mu pin u pin, and we'll set our initial state of our pin to off, which is what it will be when we get everything set up. So that'll be just pin off there, and we don't actually need to do anything else for those. What we will need to do is actually go in and initialize the pin, which we'll do in a moment. We're also going to just quickly create a destructor for this as well. So just so that we've got that ready to go to come in and basically set the pin back to an input, and as it is when prior to us actually initializing it. Brain's not working 100% today, but let's see how we go. Init type def. That's better. And we're just going to call it GPIO init. So much like we did in our main.cpp, we're basically just going to fill out the GPIO init structure using the details that have been provided to the constructor, and then we'll go through and initialize the pin. So that will be GPIO init pin equals u pin, GPIO init, we'll do mode next. So GPIO mode output push pull, GPIO init pull. We're not going to be using the pull up or pull down, so that's just going to be GPIO no pull. And GPIO speed, and we're just going to go with the slower speed for this one. So that will be GPIO speed frequency low, like so. And we'll initialize that one. Now we need to provide this with which GPIO, which is this one, and a copy or a pointer to the init structure, like so. And that will get our pin initialized. I'll leave that as is for the moment. We come into our output, and so there's a couple of different ways we can do this. If we have a look in here, not quite the file I'm after. We actually want the header file version of that one. So into our drivers, our driver, and where are we? There we are. We come down here. We can either go with using HAL GPIO dinit to deinitialize the pin. Alternatively, we could also go with just going through and setting up another init structure with the particular mode that we want that pin in. So for example, we can just go through and change that pin to an input with no pull up or pull down, and it's basically going to get us back to where we are prior to initializing it. So we might grab hold of this one, and we're just going to change this to inputs. And essentially it's going to do the same thing as a dinit. The pin is still going to be in its basically default state once that destructor gets called. Now we're going to need a few other methods in here. So we want to be able to turn the pin on, we want to be able to turn it off, we want to be able to toggle it. We also want to be able to retrieve what state it's in. So we're going to create some methods for that. I'm just going to call, this will be a void, and we're not going to be passing it anything either. So that'll be that one. One to allow us to toggle it, and then one that's going to return a pin state, and we'll just call him get state. Alright. Now, as we've done in here, we're just going to be using the HAL GPIO write pin in order to set what the pin state is. So that is going to go into here. And because we've got our MP GPIO and MU pin, we can just use those guys here. Makes it nice and easy. MP GPIO and MU pin, and we're just using these GPIO pin set and GPIO pin reset in order to set what the state is. So that'll be that one to turn it on. Now we also, because we're keeping track of what state it's in, we also need to update our m_e state variable as well. So that will be pin on, and we're just going to copy and paste this stuff down to here, and change this one to off. Now with our toggle methods, we're basically just going to check what state we're currently in. So me state. Now because we've created our enum so that pin on is equal to 1 and pin off's equal to 0, this is equivalent to actually going me state equals pin on, but we're not going to bother putting that in there because it's kind of redundant. It's still going to do the check exactly the way that we want it to do it. So we're going to go with using the other methods that we've created there. So if it's currently on, we want to turn it off. It's currently off, we want to turn it on, which makes all of that nice and simple as well. And then this is also going to be a really simple one. We're just going to go return ME state. It's always that little bit more difficult to type when you're on stream. So awesome, that all looks good there. Now what we might do is actually test that this works and replace our previous code with this one. So if we go into here, we're going to just get rid of all of this stuff. Like so. And just for testing for the moment, we're just going to create a couple of globals here. And we might also want to include that driver file. So qad_gpio.hpp, and so we're going to want a qad GPIO output. Pretty sure that's what we called it. We did. Awesome. Now we're going to make this a pointer to the class, and let's call this GPIO user LED red, and we're going to create another one which will be our green LED. Like so. And then in here we're just going to go GPIO user LED red equals QAD GPIO output. Now we're going to pass it the defines that we've got in our setup.hpp file. So if we pull that one up, as we can see the GPIO and pin numbers that we popped in here last time. So for our red one, we'll just grab that, copy that over here, and QAD user LED red GPIO pin, and GPIO actually might help if we put a new operator in there, otherwise that's not going to do what we want. User LED green, this new QAD GPIO output. QAD user LED green GPIO port. Alright. Just like that. Now we want to make sure that that works, so let's get our green LED flashing using the new class. So actually we're accessing a pointer, so we're going to want to do it with that one, and we're just going to go on. We'll use the same delay as we did before just for the moment. And delay, just so that we get that same 1 second delay there. Now, I'm just going to make sure that that builds correctly. Three errors. All right, where are we? Ah, okay. So in here, we should actually be using m_u pin. Like so. And then once that's finished compiling, we will dump that guy onto the discovery board, and we should be seeing basically the same result as we're getting at the moment. So it's the 1 second flashing LED. In fact, to change it up a bit, why don't we Oh, we actually have an error here as well. Right, might help if we actually had to type that in there properly. Beautiful. Excellent. Let's pop that onto the board. And there we go. Now, just so that we can definitely confirm that it is working properly, why don't we go with the red one, and let's just make them alternate just for the fun of it. And we'll see what that does. Might help you save the file before telling it to do that. There we go, and we have alternating green and red LED. Wonderful. So we know all of that works well. Now, the reason why I like being able to use the classes for even stuff that's that simple, that we don't necessarily need a class for, is we can just reuse that same class for as many LEDs or GPIO outputs as we like. We can also do the same thing for our GPIO inputs as well. So we're going to have a bit of a look at that. But first, what we might do is look at moving this code out to our CPP file so that we've got our declaration in the header, but all of the actual function definitions are being done in the CPP file so that everything stays nice and neat. So let's grab all of that. I'm going to pop that into this file here. Let's fix up our indents. And we're also going to need to sort out these so that it knows that those are members of this class. Might help if I had have actually copied that in there correctly. Let's try that again. There we go. No, still didn't get it right. Put that bit in the wrong spot. Awesome. We're also missing a couple of these guys. Let's grab those, pop those across there. And we're also going to just tidy this up a bit. So we'll go QAD GPIO output and just going to call it that for the moment. And again, these comments are basically just to help break things up a little bit visually, make it a bit easier when we're going through and trying to find things. Let's pop their names in here. I also forgot to chuck those in there, and for this one as well. Now, for our pin state here, because that's something that we've actually put inside the class here, it's not going to be able to find it at this point because we're currently outside of the class declaration. So we're also going to need to just pop the QAD GPIO output there just so that it knows that pin state what we're referring to is actually a member of that class. So finish off these names here. And the code from this stream will also be going up freely available on GitHub as well. So if you want to just be able to download it and have a bit of a play with it, you'll be able to do that. Okay, excellent. That's all looking good. Now what we're going to have to do in here is turn these guys into declarations, like so. Now, sometimes I like to take this approach to get everything done in the header first before actually moving stuff out to the CPP file. Sometimes I'll do it the other way and do all of the definitions straight away in the header file and write all of the function definitions straight into the CPP file. Kind of just depends on how I'm feeling at the time. Either way tends to work. Just make sure that that one builds for us. There we go. All right, and we know that one's working, so we're just going to go QAD GPIO Input. And one of the first things I like to do when I first start to set out a class is just put a private section and a public section. Typically, most of the member variables I'm going to pop in this private section, and then constructors and member functions will go into the public section. I will sometimes add other sections like I did up here for this public section. That's just so that this enum is kind of sitting in its own area. We also want that to be public though, because stuff outside of the class is going to be able to need to access that particular enum or that type, especially so that it can understand what sort of, if it uses get state and it returns that value, it's better able to access that type, if that makes sense. Alright, now for this one, it's going to be pretty simple as well. So we're going to need a GPIO type def, and we're going to need to know which pin. Now we're not going to need a pin state thing in here, simply because we're going to be retrieving that directly from one of the HAL functions for the GPIOs. So it's going to be a fairly similar thing, and again we might just whip this up in the header first, just so that we've got everything all in one place initially, and then we'll go through and pop that into the CPP file. Now, one of the other things we haven't really done is any protection in this output class to be able to check whether or not the initialization has succeeded correctly. Generally, I find that the GPIO initialization tends to go pretty smoothly as long as you're giving the right values. But some of the things that we could come back and actually pop in here at some point would be to check whether that particular GPIO, that pin, is actually being used already by another class. So we could use a static variable to be able to track which ones are being used, or a set of static variables, which is something that we might look at doing for the UART driver when we do that shortly. But for the moment, I find this tends to work quite well, and been using it a bit and not having any issues. So let's create our destructor for that one, and we're going to go void get state. Actually, we might We might just copy and paste this enum down here as well. And I'll call this pin state. And that's going to be a void there because we're not going to need to pass anything to that. Now, much as we did before, we're going to initialize our member variables. So that one will be pGPIO, and we're going to have mu pin, like so. That will get that sorted. We're also going to need to pop in our initialization code. Just copy and paste that from our CPP file from our output class. And we'll pop that in there like that. Wonderful. Now we're going to want an input for this one. So now the other thing we could come back and do if we wanted to at some point is add the facility to this class to be able to change whether we're going pull up, pull down, adjust our GPIO speed, things like that as well. For the moment, we're going to keep it a little bit simple though, and that sort of stuff can be added a little bit later. Now, copy that one, just so that we can come back and modify this later. We are just going to pop that in the same as it is in the initialization, but we're going to have this here so that we can actually see what it's doing. We don't necessarily need to actually go through and reinitialize the pin with these settings because it's already got them from the constructor. But like I said, when we go back to start modifying things at a later date, it's going to make it a little bit easier for us to see that, yes, that's what the destructor is actually doing. And with this one, we're going to jump over to here, and we can see that we have a HAL GPIO read pin method, which returns us a GPIO pin state. And we've just got to pass that, the GPIO and the pin. If we go to the pin state, we can see that we have the same ones that we use to be able to turn the output on and off. So GPIO pin set and GPIO pin reset. So here we're just going to go if HAL GPIO read pin MP GPIO mu pin equals HAL memory's failing me, so GPIO pin. Yeah, awesome. Like so. And for this one, we might actually just get rid of the else for the moment, because if it is set, then we're going to return pin on. Otherwise, it's going to come out of the if statement and we'll return pin off, like so. That's basically all we're going to need there. Now we're going to pop in some defines for our user button, and we're going to test and make sure that that is actually working properly. So if we jump over to here, I don't actually have it in this one. Okay. Off the top of my head, I don't exactly remember which GPIO it is, so we're going to track that guy down in a moment. User button, GPIO port. We'll just get this laid out so we can easily come in and add that in a moment. GPIO pin. Now we might just open up another copy of this, which is going to point me in the right direction for that one. This one, I believe, is going to have it in. Got a million projects laying everywhere, all over the place. Thankfully, it tends to be easier to reference my old code than to actually go through all of the ST documentation. Alright, so you'll see that most of my projects are laid out fairly similar. Some things change over time, but it's good to have that little bit of consistency. I actually got the setup in a different folder for this one. So grab this one, and we're going to pop that into here. So that one is GPIO, GPIO, nice easy one, GPIO pin 0. Now, one of the other things that we'll come back and take a bit of a look at some point as well will be setting up external interrupts for some GPIOs. So, for example, this allows us to do things like being able to hit the user button and trigger an interrupt request so that we can jump to that if we need to, and that can allow us to do certain things that we may not as easily be able to if we're going through and actually polling to see what the state is. So what we might do here is create a class instance for this. So we're going to go create a GPIO input. Again, we're going to make it a pointer to that one, and we'll call this GPIO user button, and create this one in here. Like so. Just make sure I'm getting that correct. Like so. Now, again, we just want to test it and make sure that that code is actually working correctly. So what we might do is come in here and we'll go get the state from that one, so that if that's on, we might make the delay different than if it is not on. So that way, if we're actually pressing the button, then we will get the LEDs alternating at half the speed. Like so. And that all looks good there. We need an else in there, that would help. And let's build that. Okay. Let's do it this way then. Create a GPIO input pin on, and we'll pop that down there as well. Let's try that. Still doesn't like it. Oh, okay. That was a bit silly. We're actually calling a member function. We need to put some brackets in there. That would be helpful. Still wants to give us an error. Well, let us do it that way. Let's see. Why is it not allowing us to do that? Have we messed up something in the class, maybe? That actually looks good. I've set that as an input, and we're creating it as an input. Okay. Aha. Okay. Silly mistake. Let's try that. That was definitely an invalid use of pin state that we had going there. That makes a little bit more sense. All right. Helps if we're actually calling the method that we're trying to access. So let's chuck that onto the discovery board. Hopefully this sort of stuff's not too boring. The main reason why I wanted to go through this, as well as all of the project setup stuff in the previous stream, is because it's kind of not only laying the groundwork for where this project's going to be going, and some of the features we're going to be adding to it as we go, how we're going to lay things out, but also just so that anyone that hasn't really played with these boards can actually get a bit of a feel for this particular approach for doing it. And this sort of stuff with the GPIOs can be used with basically any of the STM32 family. In fact, doing it this way you can use with Arduino devices and all that sort of stuff as well. So we've got that code on the board. If we hold down the user button, we can see that the LEDs actually slow down. If we let go of it, it'll speed up again. So we know that that is actually working. All right, wonderful. Now, the other thing we might just quickly take a look at is actually getting some frame timing. There's something I call frame timing set up and running, and I guess that's a name left over from the days when I used to spend my time doing 3D graphics programming in Windows, because I look at the processing loop for a microcontroller similar to how I would look at the rendering loop for, say, a game engine or 3D graphics engine. So if I refer to frame timing, I'm basically referring to the timing of the actual while loop. So as mentioned before, because we're using the HAL delays in here, the whole time that it's delaying, we're basically completely wasting what the CPU is doing. It could be doing other jobs while still maintaining the particular delay that we want for the LEDs. So we're going to look at a way where we can actually track how long it's taking to iterate through the loop each time. And then we'll be able to do things like, say, we want the LED to turn off and on every 500 milliseconds, so it will actually look at doing what we need it to do there. Kind of make a bit more sense once we get a bit more into that. Now we're going to need to pop in a couple of global variables for this one. We're going to be using uint32t, so 32-bit unsigned variables, and let's call this QAD for frame timing. We're going to need a few of these, so we're going to go QAD tick old, QAD tick new, and again, let's make our life a bit simpler. We're just going to copy and paste some of this from here. Here's one I prepared earlier. And we're going to dump that into the start of our while loop, and I'll go through and explain exactly what this code is doing. So just going to change this a little bit so that we get rid of the C2X at the start, and we're just going to replace that with QA, like so. And I forgot one of these guys up here. Might just rename these to match the code that we've copied in as well. Like that. Wonderful. All right, so we also want to prepare these variables prior to actually beginning the loop. So to do that, we're going to we're going to get rid of that there. Might help if we get all of the spelling correct. So we're going to go with QAD new tick equals how, I believe it's get tick off the top of my head, QA old tick equals QA new tick. So that way we're basically just putting the current tick value into both of those guys so that those values are set up ready for things to jump into the loop and work correctly. So we can see with each iteration through the while loop, we're going to be getting the current tick and putting that into our current tick variable. Then we're going to be comparing that to the new tick from the last iteration, and basically just to check and see whether at least 1 millisecond has actually passed since the previous iteration. Because basically if 0 milliseconds have passed since the previous iteration, then we're just going to pop a 0 into this guy. So the QA_FT ticks will actually be holding the value of the amount of milliseconds that have passed since the previous loop, so that we can use that to calculate other things as we go. Now, we've also got these guys. So basically, if it has been at least 1 millisecond since the last frame or the last iteration through the loop, then we're going to go through and put the previous new tick, that's going to become the old tick, and then we're going to take the current tick that we grabbed up here and we're going to put that into new tick. So that way we can actually look at the difference between the old one, which was from the last frame, what value it was at that point, and where we're at this time, and calculate the difference, which will then allow us to figure out how many ticks have actually passed. In this case, each tick is 1 millisecond. Now, we could just look at keeping this really simple and commenting all of that out. And if we were to just go QA FT ticks equals the new tick from this iteration through the loop minus the old tick from the previous iteration through the loop, you're probably not going to run into any issues, with one exception, and that's that there will be a point if you're designing something that's you want to be running 24/7 without issues. You will find that with the 32-bit value and that representing the number of milliseconds, I believe it's about 52 days where you will get to a point where you'll actually get the 32-bit value overflowing or rolling over to a 0, which means that if it then goes to calculate the next frame, you're going to run into an issue. Some of the projects I've worked on need to be in a situation where that device can run 24/7 without running into that sort of issue. In fact, off the top of my head, I believe there was actually a recent issue with one of the Boeing aircraft where they actually had the exact same thing. It was a 32-bit value tracking milliseconds, and it's gotten to the point where they actually had to implement a workaround because otherwise there was going to get to a point where the computer systems on the plane misbehaved because the 32-bit value overflowed and then the computer system didn't understand what was going on. So even if we're designing something where it may only be running for 5 minutes, it's worth just popping this in here anyway, because that way if we do decide to turn it into something that's going to be running for a longer period of time, it's going to be fine. So, and we can see I have actually popped in comments for that as well, just to kind of remind myself why we're actually doing this. So dealing with any situation where the loop's actually going faster than 1 millisecond in between each loop, as well as handling the 32-bit overflow that we just mentioned. So what that's going to give us at this point is this ticks value, which is going to show us how many ticks have passed since the previous iteration. So we can then make use of that. So let's create a couple of other globals here, and let's treat the green LED on the board as if it's basically our heartbeat. It's the thing that's going to be showing us whether or not the board has actually frozen. So, and just having a look at OBS, it looks like it's decided to have a similar issue with the camera as well, because it's not showing the LEDs flashing. I do have some upgrades coming as far as the stream setup, so that should be getting fixed soon enough. Let's see if we can sort that out now, however. It seems to work fine for a little while and then just decide that it doesn't want to do it anymore. No, it doesn't look like it wants to behave, but that's fine. Well, just get rid of that. I'm actually using my iPhone with an app on it to act as a webcam at the moment. We'll be looking at replacing that with an actual decent webcam that OBS is happy to play nicely with. But for the moment, just kind of threw together a bunch of bits and pieces to create a bit of a rough streaming setup. So with this one, let's get back to where we were. So we're going to call this heartbeat ticks. There we go, and QA FT heartbeat tick threshold, like so. This one will actually make constant and set it to 500. So our threshold will be the point at which we trigger the heartbeat to be updated, essentially. So our heartbeat ticks value will actually be tracking what current tick it's at for our heartbeat, and then this one will be the threshold at which it triggers and does the update. So we'll just pop that in here for the moment. So we're going to go QA heartbeat ticks. I'm going to add the QA ticks to that one, and then we're going to check if this has exceeded or is equal to the threshold value that we've just set there. Like so. Now, if it has exceeded that, then we know at least 500 milliseconds has passed since we previously updated the heartbeat. So we can then go in here and we're just going to go GPIO user LED. I'm going to use the green one. So we go green, and we're just going to toggle that. And then we also need to update our heartbeat ticks value so that it's good to count up for the next 500 milliseconds. So what we'll do is we'll subtract the tick threshold from that. So QAFT heartbeat tick threshold, like so. Might help if we don't delete the curly brace that we need there. So we're just going to pop in a note there just to say that we're updating the heartbeat LED like so. Let's see if that builds. Alright, no errors. Let's see if okay, so the camera's reconnected, but it's still not giving us the flashing that we're looking for. Pop back to that one for the moment. Let's download this onto the discovery board. Like so, and just so you can see that it is actually doing what we need it to do, jump to that one, we can actually see that we have the green LED flashing right there. Wonderful. Alright, now what we might do next is have a bit of a look at getting UART up and running again so that we can get some serial data back to the laptop in order to help aid in debugging. But we might actually end this stream now and look at getting that done in another stream, maybe in about 15 or 20 minutes, just to see if I can actually get this camera issue sorted out, and we can go from there. So thanks for watching, whether you're watching on Twitch or YouTube. I hope you found this a little bit interesting. Again, it might be a little bit boring because we're still very much looking at some of the basic stuff, but just so that you guys can get a feel about the way that we're going to be doing some of the code moving forward, and the way things will be laid out, give you a bit more familiarity. That's a mouthful. If you liked this, please follow me on Twitch or hit like and subscribe on YouTube. Also, if you would like to help support the Twitch channel and YouTube channel, and in general what we're trying to do, trying to make things a little bit more accessible to people for microcontrollers and allow people to do more powerful stuff than simply making an LED flash. So actually getting microcontrollers to really do tasks that are actually useful. It would be great if you would jump on Patreon and support us. All of that is just going to help us to provide better content moving forward and get a bit better setup where we can actually not have cameras misbehaving partway through a stream. So thank you again. Hope you enjoyed it, and we will look at getting the next stream happening in about 20 minutes. Thanks for watching.